Hi, I'm Whitney Espich, the CEO of the MIT Alumni Association, and I hope you enjoy this digital production created for alumni and friends like you.
Well, welcome MIT alumni and friends to Tech Reunions and our session on the MIT Solar System exhibit and a tour of it led by Professor Richard Binzel. A couple of housekeeping notes before we start. I'm Joe McGonigal in the MIT Alumni Office. Pleased to be moderating today. And we are live captioning this event. Captioning is available by clicking on the closed caption button. We will take your questions during the event. Please use the Q&A button on your Zoom toolbar to ask them. And we will run for the hour. And if you did not show up for the MIT Solar System exhibit tour, but we're instead hoping for another program, please revisit techreunions.mit.edu to find your way. We hope everybody is doing well, and we're really delighted to start today with Professor Binzel. He is Professor of Planetary Sciences at MIT in the Department of Earth, Atmospheric and Planetary Sciences, and he is Margaret McVicker Faculty Fellow as well. Professor Binzel, take it away.
Thank you, Joe. Thank you, and welcome everyone. It's a pleasure to have you, and we'll take this brief interlude to get our Zoom share up and running, as we're all used to now at this point. All right, so let me just adjust my screen. And there we go. All right, so Joe, thank you for that introduction. And again, welcome everyone. I want to talk to you today about an exhibit that we have at MIT. And this exhibit is on the third floor of MIT's Infinite Corridor. And we call this exhibit MIT's Infinite Solar System. And I can make the Zoom progress. Here we go. And as a teacher, you know, it's one of the things we want to try to teach is a cosmic perspective. And I think one of the hardest things to teach is the scale of the universe and to teach about our place in the universe. And I wanted to figure out how to do this in a very MIT way. And when you think of trying to do this in an MIT way, I wanted to try to find a pedagogic way to involve science, architecture, art, and engineering. And so I formulated in this class called 12400, which is now called our Space Odyssey, that I've been teaching for nearly 30 years and recently handed off to a junior colleague named Julian DeWitt. But we really like to start the semester with a really simple homework question to try to have our students and try to help all of us understand the sense of scale in our solar system. And so the simple, excuse me, the simple homework question is, if the 200-meter length of the infinite corridor were scaled to the distance of the sun to Pluto, how big is the sun, and where or how far away from the sun would you place the Earth? So think about that for a minute. So here's the infinite corridor, and we chose the third floor of the infinite corridor because the universe aligns with MIT twice a year in November and February, which is where the setting sun comes down the third floor of the infinite corridor. And we, of course, call that MIT Henge. And so that was the rationale for choosing the third floor of the infinite corridor. Okay, so we have this, this question of trying to imagine the scale of our solar system to be the length of the Earth, of the infinite corridor, and then trying to imagine how big would the sun be and how far away would the Earth be. So then again, so that's the foundation of this exhibit, MIT's Infinite Corridor. And so we can basically start to see the answer as soon as you walk into the third floor of the Infinite Corridor from Lobby 7. You can almost immediately see the answer because remember, Pluto is all the way at the far end of the Infinite Corridor. And therefore, the inner solar system is right there where we start, right in from Lobby 7. And as you step into the exhibit, you see the terrestrial planets, the inner solar system, all tightly compact right there in front of you. And so we go from the sun to Mercury, Venus, Earth, and Mars. So again, the spacing of the planets as you see them in the exhibit is their exact spacing to scale, assuming that we put the sun on one end and Pluto at the other. So let me explain a little bit about how this exhibit works. So each celestial body has a panel. And at the top of the panel, we have a 3D printed model of the object in question. And these 3D models are based on actual spacecraft data. So here you're looking at a spacecraft image of the sun that we captured and then turned into this 3D printed model. And then at the bottom of each panel, and it's a little difficult to tell without standing there in three-dimensional space, but the bottom of each panel is actually sort of a wedge shaped that kind of juts out from the wall, just to tell you that we're talking about the scale here. At the bottom of the panel, we give all the information as if it were to scale in the infinite solar system. And so the first answer to our short homework question is that if we fit our solar system, sun to Pluto, in the infinite corridor, the sun is the size of a golf ball. And so that's what you see, that orange sun there at the bottom is actually the sun to scale, fitting our solar system into the infinite corridor. And so the sun is the size of a golf ball. And you can see the little specks to the left of the sun for the sizes of all the different planets. And so this is beginning to give you the sense of how we construct this exhibit. And the scale factor to fit everything into the infinite corridor is a factor of 30 billion. So we've used the math to divide our solar system by a factor of 30 billion to get everything to fit. And so as we walk down the corridor, we need only go 1.9 meters till we reach Mercury. So you see, again, the inner solar system is really very tight. And, at each, as we see at each planet model, we repeat that little wedge at the bottom. And at each planet model, we repeat the golf ball size of the sun that you see at the bottom. And there's a tiny arrow there pointing to a tiny speck, which is the scale model size of Mercury in this infinite solar system model. But rather than just have a bunch of specks on the wall, again, we have these really nice 3D models for each planet, again, based on the latest spacecraft data. And so we can begin to see something about each planet as we go along in our tour. And in this 3D model of Mercury, you can see that it's a heavily cratered ancient world that once formed really has just been there near the sun, being bombarded by leftover planetesimals and asteroids over the 4.6 billion year age of the solar system. Now, there's a very MIT thing about Mercury. Because it's so close to the sun, astronomers always thought that the tidal pole of the sun would always keep the same face of Mercury always pointed at the sun. And that was really just kind of an assumption, and there was really just sketchy telescopic data to support that. But the MIT thing about Mercury is that radar was used by MIT professor Gordon Pettengill, who sent radar signals from Earth, bounced off Venus, got the received signals. And from that radar data was able to tell that that Mercury's actual rotation rate is 59 days. And that's an interesting number compared to Mercury's 88-day orbital period, because that means that Mercury rotates 3 times for every 2 times that it orbits the sun. And so it's something we call a 3-to-2 resonance. So again, that was discovered by MIT professor Gordon Pettengill, who lived to the age of 95. And actually, we just lost him earlier this year. All right, so let's head over to Venus. We're going about 3.5 meters away from the sun now. And Venus is a really difficult planet to explore. It's a very unfriendly world. And the reason it's so unfriendly is that Venus has a very thick atmosphere full of CO2. It's a CO2 atmosphere with a pressure of about 90 times that of the Earth. And with all that CO2, that's a greenhouse gas, of course. And so that greenhouse gas, abundance of greenhouse gas, again, 90 times the pressure of Earth's atmosphere, leads to a runaway greenhouse with a temperature of about 700 Kelvin, which is a balmy 900 Fahrenheit there at Venus. And so Venus has been very difficult to explore as a planet because it's covered in this thick atmosphere that we can never see through. But again, MIT to the rescue, and in fact, radar to the rescue. And it was our beloved Gordon Pettengill who led a radar mapping mission to Venus back in the early 1990s, and that was the Magellan mission to Venus. And there was a radar, basically a radar imaging system on board the Magellan spacecraft that gave us this model of this model of Venus that we see here. And what we discovered about Venus is that it's a volcanic lava-covered surface that seems, totally solidified at probably about 1 billion years ago is the last time lava flowed on Venus's surface. But we don't know that for sure. In fact, we have so many mysteries about Venus. Is it still active? Are there still active volcanoes and volcanism on Venus? Or is it completely stopped? And is the chemistry of Venus, even this odd chemistry, is it even possible that Venus might support life in this very complex chemistry of its atmosphere? And there's been a recent detection of a gas called phosphine, of which life does produce phosphine, and it quickly disassociates. And so scientists are debating whether the detection of phosphine is correct and what does it mean. So anyway, there's all these renewed questions about Venus, and you may have heard the news this week that NASA just announced that they have selected two new missions to fly at the end of this decade, which will go to Venus. One will study its atmospheric composition, and one will study its surface composition. So Venus is literally going to get its day in the sun as we go forward in this decade. And anyway, so it's part driven by the science of Venus, but also our technological capability to basically overcome the harsh environment of studying Venus. That's now bringing Venus exploration back to the forefront. All right, so we get to Earth. All right, so the question at the beginning, the homework question at the beginning was how big is the sun and how far away is the Earth? And that's answered there on the Earth panel, where you see at the bottom that we are 5 meters from the sun, and you see maybe you can make out a speck of the Earth superimposed on the sun, so we get a sense of this scale. So we've answered our homework question of the sun and Earth, but we'll keep going throughout the solar system. So again, as every stop on our tour, we have a 3D model of our planet, and here you see the familiar 3D image of the Earth. And because we were individually constructing each of these planetary models, we could orient it any way we could. And if you take a really close look at our orientation of our Earth model there, you might notice that we've centered it on Cambridge, and we didn't center it on Central Square or that other subway stop. We made sure to center it right at Kendall Square. And so the center of the universe, as we all know, is MIT, and here it is in the Infinite Solar System exhibit to prove it. So we have something also interesting that you might be able to make out in this image about our Earth model. And that's where in the scale part down at the bottom, you might see an ellipse. You might be able to barely make out an ellipse that is sketched to scale on the golf ball sized scale of the sun. And that ellipse is the orbit of the moon. And so it's very interesting and in fact humbling to think about how far into space have humans traveled. And we, of course, have the farthest we've gone to space is the moon. And so in the scale of our solar system, and in this Infinite Solar System exhibit, the furthest distance in space that humans have traveled is only 1/2 inch away from the Earth. So we really still are at the very beginning of our exploration of space, still really yearning to leave the Earth-Moon cradle and go out and explore further. And of course, the object of, when we think of human exploration, expanding beyond the Earth-Moon system, we always think of Mars. And there's a lot of reasons why Mars gets so much attention. First is it's much more hospitable to spacecraft and to humans if we were ever to go there. But the other reason that Mars gets so much attention is that it, for some early period in its history, had a climate that was conducive to holding liquid water. And so we kind of joke about it among ourselves that every week NASA discovers water, that there was water on Mars. This is something we've now known about for decades. But we find different lines of evidence and different things about the water on Mars, which is why it keeps coming up in news stories. But to be fair, the reason why water on Mars is so interesting to us, because for life as we know it, water is a requirement. And so the idea is, if we want to understand how unique we are on the Earth, how unique is life on Earth, we need to go and see if life did evolve or could evolve elsewhere. And of course, the place to look best is our own solar system. And so really, when we go to Mars and we're exploring the early wet climate history of Mars, we're really trying to understand ourselves. We're trying to understand our own origins and understand, just how unique we are here on Earth. How unique is life on Earth? Some of the features that you can see in the 3D model of Mars are this giant canyon on Mars called Valles Marineris, which formed in the early stages of the crust of Mars was cooling and contracting. And then you can make out volcanoes on the surface of Mars. The largest of these off to the left is Olympus Mons. It's about the size of the state of Arizona. And these volcanoes spewing out gases probably led to the early thicker atmosphere of Mars, allowing water to be stable as a liquid on the surface. All right, so we are going to leave the cozy confines of the inner solar system and head out between Mars and Jupiter. You may know, of course, is the asteroid belt. And it's really very interesting. The asteroid belt is nothing like Star Wars, where it takes a daring pilot to survive passage through the asteroid belt. In the real asteroid belt, the average spacing between any two asteroids is about 1 million kilometers. So it's not a particular navigational challenge to get through the asteroid belt, though NASA always checks just to make sure there's not something on our way, in our way. And if there is, often we'll turn on our cameras and use that asteroid as a little calibration target. So anyway, the asteroid belt, just to remind you, is really just leftover building blocks, leftover planetesimals from the very beginning, the very formation of our solar system. And the reason why a major planet never could bring itself together in the asteroid belt is because the next planet out, Jupiter, is the most massive planet in our solar system. And Jupiter acted as a perturbing force, sort of as a bully in the neighborhood that disturbed the orbits of all the material that was trying to collect itself in the asteroid belt. And so a large planet was just simply never successful there. And we're left with leftover pieces. But scientifically, that's fantastic, because the asteroids and the meteorites from which that come from asteroids that we can study in our laboratory are a chance to have time capsules of these building blocks for how we built planets. And so it's a fantastic opportunity for scientific study. In our solar system model, we've projected the data for the largest asteroid in the asteroid belt. That's Ceres. It's about 1,000 kilometers across. And you can see it's a cratered body. And you can also see that it's not quite spherical. And that's because at 1,000 kilometers in size, that is just about the limit for gravity being able to pull a rocky body into a spherical shape. And so Ceres is right on the limit of the tug of war between the strength of the material trying to resist the pull of gravity and gravity itself pulling itself into a sphere. I want to make an MIT comment about this model of Ceres. And in fact, the fact that we can see the craters and the topography of Ceres is the result of a kind of instrument called a laser altimeter. And this is you put aboard a spacecraft a laser that fires pulses down at the surface you're orbiting. And you'll time from the time of sending the signal and the return pulse, that gives you an exact distance to the surface, and you can use that timing data of literally millions and millions of pulses to construct a topography of the surface. And it's MIT's Professor Maria Zuber, who is the vice president for research of MIT, who has designed and flown laser altimeters to Mercury, Mars, and Ceres, and other places that give us most of the topographic information we see for these bodies in the inner solar system. So a very major contribution to planetary exploration by MIT and MIT's Maria Zuber. Okay, we're going to leave the asteroid belt and head off to Jupiter. And to do that, we now head into building 3. And we're going to head to Jupiter. At this point, you can look down the infinite corridor. We know Pluto's at the far end, 200 meters away. And at this point, we have traveled 26 meters, or about a tenth of the distance to Pluto. And already we're to Jupiter. And so it's, again, you can begin to get a very physical intuition here of the spacing of the planets in our solar system. So Jupiter is a gas giant planet, again, the most massive planet in our solar system. And you can see just off to the side there, Jupiter's famous red spot. And one thing you might notice about Jupiter, a little bit tough in this video, but you might be able to notice that Jupiter is not quite perfectly spherical. It's a little bulged at the equator and flat at the poles. And I won't make any comment about any of us being bulged at our equator. But Jupiter it bulges out at its equator, at least, because it's rotating very fast. Jupiter rotates in 12 hours. And so because it's a gas giant planet, it can behave as a fluid, and that fast rotation allows the equator to bulge out or take on what we call the shape of an oblate shape. There's something pretty significant also here that you can see in the model of Jupiter down at the bottom, down at the wedge at the bottom, which again is the scale in the infinite corridor, is you can maybe make out the spacing of 4 large satellites of Jupiter. And you can tell with Jupiter superimposed on the scale size, golf ball size of the sun, you can tell that Jupiter is actually quite sizable in our solar system. It shows up, its disk and its size shows up relative to the size of the sun. But we see spaced out along there the orbits of 4 very large satellites of Jupiter, which were discovered by Galileo in 1610. And we call these the Galilean satellites. And the importance to the history of science to Galileo's discovery of the satellites of Jupiter was Galileo could easily deduce, and you can do this with binoculars or a small telescope in your backyard, you can easily deduce that these satellites are actually going around Jupiter itself. And so it was basically a observational proof that not everything in the universe orbited around the Earth. And so it was really the beginning of the confirmation of the Copernican model of our solar system, or the Copernican revolution. So you can see, anyway, it's really interesting to see the scale and the extent of the satellite system of Jupiter that Galileo discovered. And anyway, I think that's a really fun history of science aspect to this seeing the solar system model in the infinite. All right, so we keep going on our way. We get out now 48 meters from the sun. We're still in building 3, but we're doubling our distance from about 25 meters to 48 meters away from our sun. Again, Pluto's at the far end. And we arrive, of course, at Saturn. And, the thing about Saturn that we all know and we all recognize is the really spectacular ring system that Saturn has. And so in this model at the top, where you see our 3D image of 3D model of Saturn, we also include the rings. And the ring system that you see there is in fact scaled exactly to the size of the planet that you see there. And so you can get an immediate sense of just how extensive the ring system of Saturn really is. And that ring system is composed of millions, if not billions, of tiny boulders of rock and ice that orbit around Saturn's equator. And they're kept in place by the bulge at Saturn's equator, making a dominant gravity force around Saturn's equatorial region, but also this system of 80 satellites around Saturn also shepherd the ring system and keep it in place. And it may be that the ring system was in fact formed by one of those satellites getting too close to Saturn and the tidal stresses from Saturn's own gravity tearing that satellite apart, and those pieces remain in the ring system today. The ring system is really quite impressive, and so again, you might be able to make out on the golf ball scale of the sun at the bottom, on the bottom panel, that you can again see that the size of Saturn is sizable relative to the sun, but also maybe you can see the extent of the ring system. So again, the ring system is a pretty important feature in our solar system. But the extent of that ring system is almost the same dimension, if you remember, the dimension of the moon's orbit around the Earth. So if we were to bring Saturn into the inner solar system, and it would just barely fit, Saturn and its ring system would just barely fit inside the orbit of our moon. And so you just imagine just how amazing that ring system is. And just here in this exhibit, it's a way of really seeing that and physically gaining a physical intuition on that. All right, so we're at 48 meters from the sun. We have to get out to 200 meters because way down there at the far end is Pluto. And so now we're entering into building 10. We're basically doubling our distance from the sun. You're beginning to get a sense of the scale of our solar system. And as we head off to Uranus, there's something else that's really interesting about this exhibit and our scale factor of 30 billion, because if you take the speed of light and divide it by 30 billion, in this exhibit, or a beam of light traveling through the hallway, through the infinite solar system, would go down the corridor at the rate of 1 centimeter per second. So you take the speed of light, divide it by 30 billion, you get 1 centimeter per second. And so it should have taken us about 3 hours to get to Uranus, but we've done it in about 20 minutes here. And what that means is, as we are touring the solar system, we are traveling faster than the speed of light. We're traveling at warp speed. And all I can say is, if you're running late for class, it's pretty convenient to be able to travel at warp speed to get to where you're going. And if you do the math about what is a walking pace, and you go onto the Star Trek websites and try to do a conversion, I come up with the speed of walking down the infinite corridor here through the infinite solar system is about warp factor 7. And so if you ever wanted to experience warp speed, you can do it with this exhibit. All right, so Uranus is the least massive of the gas giant planets. You can make out something of the size of Uranus against our golf ball scale of the sun. And two interesting things about Uranus. One is that it's tipped over in its rotation. It's almost flat in its orbit. In other words, its obliquity, which is the tilt of a planet's orbit, is 98 degrees. And the obliquity for Earth is, of course, 23 degrees. So Uranus is highly tipped over. And then secondly, there's a very MIT thing about Uranus. It turns out that Uranus has a ring system. So it was the first planet other than Saturn to be discovered to have a ring system. And now we know that Jupiter, Saturn, Uranus, and Neptune all have rings. But that discovery of the ring system was by MIT professor James Elliott, who was studying the atmosphere of Uranus by watching how a bright star disappeared behind the atmosphere of Uranus, something we call a stellar occultation, because the planets all move across the sky and occasionally they pass in front of a bright star. And in the course of watching that occultation, Professor Elliott saw the light blink on and off, way off to the sides of Uranus on both sides, and he deduced that there must be a ring system. All right, so we are going to continue on into building 4 here and head off to the planet Neptune. And you may have noticed when we looked at Uranus that blue color, the blue color of its atmosphere. And it may have given you a thought to the blue sky of Earth. And both come about from a similar kind of process called Rayleigh scattering. But in the case of the Earth's atmosphere, the blue sky that we see is Rayleigh scattering due to nitrogen, the way light scatters off the small molecules of nitrogen. But for Uranus, and as we get closer and closer, you'll see a very deep blue color for Neptune. Warp speed is a beautiful thing, isn't it? We finally arrive at Neptune, and you'll see the very deep sky, blue sky of Neptune. And that's simply because Neptune has a greater abundance of methane in its atmosphere. So it gives it that more deeper Rayleigh scattering and the deeper blue color. We haven't talked very much about, and again, you can see barely make out the size of Neptune relative to the sun as a gas giant. We haven't really talked about temperatures, but we are now 150 meters out of 200 in our model away from the sun. And of course, the further away you get, the colder the planetary temperatures. And Neptune is at about 60 degrees Kelvin, or just a wonderful minus 350 Fahrenheit once you get this far from the sun. All right, so we now head into the last, we're heading into building 8 and heading towards my favorite planet. I love calling Pluto a planet, which is, of course, Pluto. And, at the speed of light, it should have taken us 5 hours to get from the sun to Pluto. But again, the beauty of the exhibit and warp speed is we can get there in just a few minutes. And Pluto is very personal for me because I've had the privilege as a planetary scientist to be studying Pluto for almost my entire career. And in the course of that career, we've defined sort of the science objectives. What are the mysteries about Pluto? And then spent a decade advocating and building the consensus that Pluto should be explored by a spacecraft. And so we were finally successful in 2006 to get a mission to the launch pad called New Horizons, a NASA mission that we launched in 2006, which began a 9-year journey across the solar system to reach the planet Pluto. New Horizons was the fastest spacecraft ever launched by any spacefaring nation. And still, it took 9 years to get to Pluto. So imagine taking 9 years to walk the length of the infinite corridor. That is how fast the fastest spacecraft that we can ever launch can go. All right, so we finally reached Pluto in 2015. And what did we find? Well, what we found absolutely amazed us. We found, in spite of all the bad things that happened to Pluto, that Pluto still has a heart. This heart-shaped region is called Tombaugh Regio, named after the discoverer of Pluto. And the left lobe, if you will, is this flat nitrogen glacier. I said glacier on Pluto, we call Sputnik Planitia. And this is actually a flowing glacier of nitrogen ice on Pluto, meaning that Pluto is an active planetary world. There are planetary processes going on in the outer solar system, and that's just astounding to us. We expected to find Pluto sort of cold and inert and sort of a relic of this part of our solar system, but we find that Pluto is active, an active planetary world, and this is why we explore, because it totally surprised us. There's some MIT things about Pluto. The first has to do with the New Horizons mission, and that is that the two of the deputy project scientists on the New Horizons mission are MIT PhD graduates, both women, and it's Dr. Leslie Young and Dr. Kathy Olken. Are project scientists, deputy project scientists, so they're the co-leaders of this NASA Pluto mission, so something we're very proud of. And again, even the knowledge that Pluto had as an atmosphere was an MIT discovery back in 1988 by Professor James Elliott. All right, so we've sort of reached the end of our solar system, but one of the things that we now recognize is that our solar system doesn't end at Pluto. We now know that there's a second asteroid belt out beyond Pluto. It's something we call the Kuiper Belt. And there are other Pluto-sized bodies out in the Kuiper Belt. You can see 3 of them listed there. And, you know, on this scale, we would now have to go out the window of Lobby 8 in order to fit Haumea, Makemake, and Eris into our model. And similarly, the New Horizons spacecraft itself is now out the window in the lobby of Building 8, more than 250 meters away from the sun. And as we think about spacecraft exploration, you know, one of the most famous explorers of our solar system are the Voyager spacecraft. And the Voyager spacecraft, which were launched in the 1970s, are now, you know, even far beyond this exhibit. And if you calculate where they are to scale, they are now headed towards Back Bay, and they are at about the 100 smoot mark on the Mass Ave bridge, almost all the way across the river to Back Bay. So kind of fun to think about that. And if you want to think about this scale even a little bit further, if we continued on this scale, the nearest star, Proxima Centauri, would be located about the distance to Chicago. So again, it's just this mind-blowing way of trying to understand the scale of our solar system. So as a concluding perspective, we're going to get to Lobby 8 here and turn around and look back to see where we came from. And it's pretty amazing to think about the sun being a massive golf ball at the far end of that corridor. And it's the sun's gravity that's holding all these planets in their orbits. And it's really, it kind of makes you really appreciate what an amazing force that gravity is. And, you know, it's just all of the many different areas of physics that come to mind here. So with that, I just want to sum up and, you know, say that again, the idea was trying to involve science, architecture, and art into gaining a cosmic perspective. But along the way, you know, as we see the data and the understanding of all the planets that have come from spacecraft exploration, we realize that that exploration has been achieved through engineering. And I really like to think of space exploration as this beautiful combination of the mind and hands, the mens et manus. It is, you know, the science of the mind that creates the questions and the drive to explore. It's the design in the mind and the creation by the hands that builds our spacecraft. And then it's the technical capability to fly these missions. And just one thing about the technology and the difficulty or the challenge of spaceflight and space exploration, as we look at that golf ball and the Earth way down at the far end of the corridor, and we see Pluto out here, the navigation precision to hit our aim point in order to get our data at Pluto. On this scale, we hit an aim point that was precise to a length finer than the thickness of a human hair. So this really amazing accomplishment of science and engineering to accomplish this exploration of our solar system. So with that, I'll wrap up, and I want to acknowledge my co-workers in putting this exhibit together. That was Todd Robinson of MIT and Arthur Liu of MIT's Lincoln Labs. And the support for this came from Mike Sipser and Heather Williams in the MIT School of Science. And this video was created by MIT graduate student Fatima Hussein, enabling us to take this tour. So with that, I'm going to stop sharing my screen and take your questions. And thank you so much for taking this journey with us today.
Thank you, Professor Rick Binzel. That's a great 35-minute tour of our solar system, and alumni and friends joining us today for Tech Reunions. Hope you got a treat there. But if I'm correct, Professor Binzel can answer questions at warp speed too. So please put them in the chat. Please put them in the Q&A tool of the Zoom toolbar. Let's start with Walter Miller. If I'm correct, class of 71 celebrating his 50th reunion this year. Walter, welcome back. The true rotation of Venus, he says, was discovered via radar studies, perhaps in the 1960s, he recalls. Who did that research?
That again was Gordon Pettengill who did that. So I mentioned the case of Venus, Mercury. There's so much to talk about at Venus. Gordon has a lot of tribute to Gordon. We lost Gordon in just about a month ago, I believe. And he was at age 95. And Gordon also used radar to deduce the very slow rotation of Venus. And in fact, Venus is upside down and rotating slowly. And then he was a natural to bring his expertise with the Magellan, the radar mapping experiment on the Magellan spacecraft in the 1990s. So thank you for asking about Venus and helping us remember Gordon.
Question about, back to the beginning of your presentation, talk a little bit more about the scale of the infinite corridor here and getting the planets to fit just right. I'm curious if there were any good math arguments going on of measurements and what to leave in and what to leave out for assumptions or considerations.
Yeah, that's a really good question. Yeah, there's, when you design an exhibit, there's so many things that go on. Well, first, to me, I thought it was really important we fitted in the infinite corridor. There are models of solar systems all around. There's one at the Boston Museum of Science. There's one on the National Mall. So there's nothing unique about a scale model of our solar system. But what I think there is unique about this one is it's in a building, and you have windows on each end of the building. And I really like it because as you physically take the tour, you have a real sense of where you are in the solar system at all times. And you can take the tour in a matter of minutes, so it's a length of time where your concentration can kind of be uninterrupted, which is a pretty tough thing in today's overconnected world. And so to me, it had just the right feeling to fit in that building. And with the windows on each end, you always had this sense of perspective. And it was obvious we were going to put the sun where the sun comes in on MIT Henge. And then it was, the challenge of how do you get the specks to actually appear visible there on each of the models, and the way we did the wedge panels for trying to convey the scale. So, and then the 3D models were actually the idea of Lincoln Labs' Arthur Liu, who just loved making models of planets, and that was a match made by other colleagues. I actually knew Arthur and knew he was making these planet models, but somebody else had to suggest to me, hey, why don't you have Arthur put planet models with your exhibit? And boy, that was a match made in heaven. So anyway, so thanks for asking. Really interesting. I actually wrote a piece in Tech Review about constructing this exhibit. And I meant to have that URL.
I'll grab it and post it in the
maybe
chat.
You can find that and paste it in the chat. Thank you. So anyway, great question, but I did write a little essay about it. So I hope that helps you.
More questions about asteroids and think about Ceres. I think it was, how big would the planet have been if the asteroid belt would planets maybe have been if the asteroid belt had come together, ignoring Jupiter's impact on it?
Yeah. So the mass currently in the asteroid belt is much less than an Earth mass, but that's because Jupiter's been tossing stuff out, basically stirring the pot and tossing stuff out, which is why it could never coalesce. But probably if it could have been successful in making a planet, it would have been roughly Mars-sized, another Mars-sized planet in the asteroid belt.
A shout out to Moxie from Rusty Schweikart says, when we're talking about Mars, can you just explain what was MIT's role in that project?
Yeah. Oh, thank you, Rusty. So Rusty Schweikart is a good buddy and was Apollo 9 astronaut, lunar module pilot. if I recall, Rusty. And in any case, MOXIE is an experiment on the current Mars rover that is looking at how do you make, or can you make, oxygen out of the Mars atmosphere. And so it was developed at MIT, in fact, at MIT Haystack Observatory. Is the origin of the MOXIE experiment. And in fact, we have two professors at MIT, Benjamin Weiss and Tanya Bozak, who are sample scientists, and they are helping, you know, with a group of scientists as this rover explores different parts of Mars, where it might drill into the rocks and get samples that ultimately we look forward to returning to Earth. And so there is quite an MIT presence on the current Mars exploration rover, the Perseverance rover, so aptly named for the challenges we've faced over the past year or so.
On the smaller planets, Dan asks, do they lack rings because they don't have the tidal force necessary to break up a moon?
Oh, that's a great question. There's no reason why the Earth can't have a ring. I mean, we've searched for it and we don't have one. So there's no physical reason why you can't have a ring. In fact, when we flew to Pluto, we used our cameras to make sure there wasn't a ring, or if there was, we wanted to make sure we steered around it. So they can, they just don't. I think there's just, in a sense that they might have a ring, but they can't hold it because they don't have enough gravity to guard against any other perturbing forces that would want to tug the ring particles away. So yes, you can. Small planets can have rings, but they're hard to last. It's hard for them to last very, very long, and so I think that's why we don't typically find rings, or haven't found rings around small planets. So yes, they can be there, but they're hard to keep.
And what about moons? Says Dan. Why are Earth's moon and Pluto's moon so large? And does Earth have other moons?
Oh,
or Pluto, or why not?
Yeah. So Pluto has 5 moons, and the Earth. Occasionally, the Earth the passing asteroid will kind of get trapped in a bit of a gravitational hold by the Earth, but it doesn't last very long. But again, when you're in the inner solar system and you can get the sense of scale of the inner solar system, there's so much gravitational tugging of all the planets on one another that it's really hard to stay stable. But the Pluto system, again, has 5 satellites. We think that the Earth's moon, which is very large, and Pluto's moon, Charon, is half the size of Pluto itself. It's the largest moon relative to its primary planet in the solar system. The Pluto-Charon system is almost like a double planet because the center of mass is in between the two bodies, and the center of mass in the Earth-Moon system is inside the Earth. So the barycenter in the Pluto system is in between the two bodies, like double stars. And we think it was the best mechanism we have for how you form such a large moon is actually the impact in the early formation of the solar system, where their bodies are forming and there's lots of planetesimals around. Sort of the end of, as the planets are kind of in their final stages, maybe some large leftover planetesimal hit the Earth, splashed off the material that formed the moon. And similarly, that could have happened out in the outer solar system with Pluto.
So Jeffrey asks, do we expect even more moons to be discovered within our solar system?
Absolutely. Saturn has 80, there's 1 or 2 moons discovered every year. Jupiter, I've lost track of the number of moons of Jupiter. Those get discovered every year. So, and a lot of those are captured asteroids and things like that. So yes, there are certainly more moons to be discovered.
From Craig Richardson, in this model of Pluto, is Pluto shown on its aphelion? In this model, it's much farther from the sun than Neptune.
Yeah, so we actually show it at its semi-major axis distance, which is 40 AU. So we show it at its average distance from the sun. In fact, all the planets have slightly eccentric orbits. So that is, they're not circular, they're slightly eccentric orbits. Mercury's very eccentric, Mars is very eccentric. Earth's orbit is only about 1% eccentric. In other words, out of round. And we chose to put the planets at their heliocentric semi-major axis distance, or their average distance over the course of one orbit. So that was a factor that someone could have mentioned in the previous question.
Other questions about the scale. What if the Oort cloud, if the model had the Oort cloud at the end of the corridor, how would that have affected things? If the model had only gone to Neptune, how would that affect things?
Yeah. So, then we'd have the challenge of, if we wanted to put fit to the Oort cloud, then the whole inner solar system, probably would have been like in building 7 or building 3 in order to get the Oort cloud out. So again, the sun to Pluto seemed to give that kind of 5-meter spacing of the Earth, so the Earth wasn't nose pressed up against the sun. That wouldn't have been very, very satisfying. And so the 200 meters to sun to Pluto seemed right. So just a quick question about the exhibit. So I gave this homework problem for 30 years, and I always said, and if someone wanted to sneak out in the middle of the night and construct this, I'll never tell. But I never had any student takers, and so I ended up sneaking out in the middle of the night and making little blue chalk marks right along the floor of spacing this out and really getting a sense of feeling. And once I did that, I said, oh my gosh, we really got to do this as an exhibit, because it's even for someone who lives and breathes this stuff, it's very enlightening to kind of being able to exist in that physical space.
Some New Horizons questions from Scott. Given the distance of the spacecraft, even during the mission, but definitely now, what's the time to get messages back to Earth? And talk a little bit more about the what we learned about Pluto from the New Horizons surface specifically.
Yeah, thank you. So it's right now, I think it's about 6 hours each way for a message to and from the spacecraft. But it was about 5 hours each way at the time of the Pluto encounter. What that means is everything has to be pre-programmed. We can't get there and say, hello, how are you? What's it look like? Could you send us a picture, please? We'll look at the picture and have it take another one. Everything and it was a flyby, because we could not, even on the largest rocket, we couldn't have a spacecraft carry enough fuel to slow down and stop once it got to Pluto. So it was a flyby. So everything had to be pre-programmed, and we practiced and almost like literally like a ballet of pointing the spacecraft to take all the data. And it had to work, because we got one shot and one shot only, and it worked. It worked flawlessly. So other things about Pluto is this glacier, this nitrogen ice glacier, has no craters on it. So we know it's incredibly young. We know it's flowing. We even think it's bubbling. We even think there are convective cells there from minimal internal heat of Pluto is actually overturning it to keep it crater free. We see regions of different ages on Pluto, a very dark region called Cthulhu, that is kind of the oldest organic rich parts of Pluto. We see heavily cratered poles. We see lightly cratered equator. And at MIT, and my PhD student, Alyssa Earle, looked at long-term Milankovitch cycles. In other words, how does the tilt of Pluto change, and how does the precession of Pluto's orbit go over multi-million year timescales? And it seems there are long-term seasons on Pluto such that the surface may have even been warm enough for liquid nitrogen. We actually see evidence of a few ponds, frozen ponds on Pluto, thinking that the atmosphere was once thick and liquid nitrogen could exist on the surface. So just a whole host of complexities about Pluto that came about from the spacecraft data, and complexities that we never even anticipated we'd see.
Couple other questions about water. Maybe you could rank what curiosities have yet to be sated for you about water in the solar system, and will we find water on other planets, etc.
Yeah, so we find water. Mars gets all the attention partly because we can get there, right, and we're good at getting there. There's a large satellite of Jupiter called Europa, one of the Galilean satellites. And when we understand how the tides, how Jupiter, the tidal stresses from Jupiter affect Europa, we think that underneath a 50 or 100 kilometer thick ice layer on the top, there's actually an ocean of liquid water on Europa. And so we think there's liquid water at Europa. that could support life. Out at Saturn, there's an icy moon called Enceladus that we just discovered has geysers coming out of the cracks in the surface. So we know there's liquid water underneath the surface of Enceladus. And on Titan, another moon of Saturn, which has a thick atmosphere, about like Earth's atmosphere, but much, much colder. Complex hydrocarbons can be liquid, and we see like river valleys of these complex hydrocarbon liquids on the surface of Titan. So anyway, I think the questions are still fundamental. You know, if there's water, does that mean life? And so we're still really at a very fundamental stage in following the water and trying to understand the processes or the uniqueness of the origin of life.
And Sandy asked about chemistry in the outer solar system. What else are you curious about there, and what are you excited about finding out?
Yeah, in the outer solar system, I'll take Pluto as my favorite example. It's really interesting, nitrogen and methane. It turns out the phase diagram for on Earth, let me just back up. On Earth, of course, we're right at a temperature for water in the phase diagram of water, where water can be a solid, liquid, or gas. And out at Pluto's distance, we're right in the sweet spot of a phase diagram for both nitrogen and methane, that they can exist as water, liquid, and gas. So it's the complexity of seeing this triple point, other planets at a different triple point for a different compound, and how that interplays into the surface structure, the distribution of where we find nitrogen, where we find methane, and how much of it at any given time is solid on the surface, like it snows out onto the surface, and how much of the time is it in the atmosphere, because Pluto has a very eccentric or elongated orbit, and sometimes it's very close to the sun, sometimes it's much farther from the sun. And so again, Pluto itself goes through seasonal cycles of these things going from solid to gas and maybe even liquid. And so anyway, a lot of really complex chemistry. So I'm fascinated by how does Pluto seasonally change. And unfortunately, as a human being, Pluto's orbit is 248 years. So these are questions that we can only write down. We have a book. I'm not plugging a book because I don't get any, it's a voluntary nonprofit book, but it's a book on the Pluto system after New Horizons that just went to press in the University of Arizona Press. And we have 20 chapters that will tell you in great detail of that. So if you look at something called the Space Science series in the University of Arizona Press that I edit as a voluntary activity, we do have a Pluto book that should be out in just a few months. And it's as complete as we can make it, results from the New Horizons mission. I never thought I was going to do a book plug here.
You are allowed to plug that, of course.
Thank you.
Robert, cramming questions in here. Robert says, at the scale of the model, how many known KBOs would be in the green building hallways? Obviously, it's a moving target.
Yes, thank you.
Can the model be extended or updated to include them?
Sure, why not? Volunteers are welcome to contribute to making that happen. That's right. So a lot of these would be in the green building. We could spread it across the campus, and we could even put Proxima Centauri in somebody's house or a museum in Chicago. I've thought about if anyone has museum contacts in Chicago. I thought about putting Proxima Centauri in the Chicago Museum, the planetarium, Adler Planetarium in Chicago, and talking about the exhibit back at MIT. Kind of been busy flying around the solar system.
One more on Ceres. You mentioned it about the limit where gravity forces a body to be spherical. If Ceres were slightly larger, what would the process look like for going from non-spherical to spherical? I.e., is the model more like sand, or do things heat up?
Well, it does heat up, but it cools down. It would have heated up in its early formation stage, but then rapidly cooled down, 4.6 billion years later. So it does flow in sort of plastic flow. And then you can have what's called viscous relaxation, so that you try to make a crater, but then the gravity wants to flatten it back out. And there's a lot of examples of viscous relaxation on Ceres. So it's right at the limit where gravity wants to win, and the strength of the material that makes Ceres is just about capable of overcoming it.
Great. Well, we're nearly at time here. I want to ask you this maybe one slightly off topic, but a more aero-astro question perhaps. Folu asks, what are your thoughts on the emergence of private spacecraft for exploration of the solar system, and will you sign up?
Absolutely. Fantastic. Competition makes the world go. And so, competition and drive and innovation are all things that are coming out of the private space sector. And I think it's fantastic. So sign me up.
Great. Well, Professor Richard Bidzell talking about the actual solar system model in the Infinite Corridor now, alums who have not been back to campus for some time. This was installed in 2017, we want to say. And when will it be open again, do we think, Professor Bidzell?
Well, the exhibit is there as far as I know. I have not walked it in a year and a half myself. So as far as I know, it's there. But once the MIT campus is open and we can visit, please come and walk it. And I'm happy to walk it with you. I never get tired of exploring the solar system.
Great. Thank you again, and thanks alums and friends for tuning in. We hope you have a great Tech Reunions week and weekend. And thank you, Professor Bidzell.
Thank you. Thank you for coming along on this journey, everyone.
Thanks for joining us. And for more information on how to connect with the MIT Alumni Association, please visit our website.